is the second webinar in a new series of monthly webinars, and the next webinar will be led by our colleague Dr. Jackie Stroud, and she will be talking about earthworms and acoustics, so listening to earthworms, and the date for that is the 19th of March at 4 o'clock. So we'll take questions at the end of the presentations, but please feel free to type any questions into the chat as we go along. So we're really delighted that Roma Gwynn has agreed to talk to us this afternoon. And Roma's taken a lead role in the development and registration of many new biorational technologies in the EU and internationally, and I'm sure a lot of you have met Roma and heard her speak before, and then Roma will be followed by Dave Chandler from Warwick. So I'll hand over to you now, Roma.
Thank you, and thank you for those kind words, Rosemary. Okay, so I'll just move everybody out of the way. Hi, good morning. Sorry, there's a slight issue with.
And just to say that Roma is in the USA, so that might account for some of the small issues.
Is there a time delay? Okay, all right. Thank you very much for inviting me to talk at this seminar webinar this morning, or this afternoon rather. Really appreciate being involved. So I'm going to give a wee overview of biological solutions for sustainable crop production. And I want to start by just thinking about where we've got to in the industry and what's happening in plant protection. So if we kind of think about going back to the green revolution of the sort of 1950s and 60s, where there was a strong desire to feed the world essentially, and there was a high input system of high input fertilizers, high input plant varieties, and high input chemical or pesticides or synthesized pesticides. But what we've come to realize over time, and if we look at this picture, it's a good representation. It's beautiful landscape. It's beautiful, but when you look at it, you realize it's a very changed landscape, and there's very little space left for nature in this landscape. And slowly we've come to the realization that maybe the way we grow food is having too high a consequence to the environment, and that, are there other ways in which we can grow food? And you look at that and think, well, the other problem we have is the pest control problem. Is we grow things in a monoculture, and that creates a really good environment for pests and diseases to develop with very few barriers. But at the same time, we know that if we have a functioning ecosystem and we have complexity, that the chances of some organism reaching an epizootic and taking over, which is what happens when we get an invasion of disease or insect, is less likely. So how do we balance that tension between having a functioning ecosystem with as much diversity as possible to create a more stable plant production system, and the desire to produce good quality food at a good price for the farmers and for the consumers? And this, for me, is where biocontrol solutions come in. But if we think about it also, we have this model, we have this high intensity model, and we know from FAO figures we're losing 30 or 40% of the crops before harvest, more than 10% after harvest. So we've got to have best practice to meet these challenges. So what it says to me, if you have a model that's failing up to 40% of the time, is that a good model? And this adds to the sort of evidence and the thinking about changing how we do crop protection or plant production. And what you can see now is that biological solutions are increasing the mainstay of sustainable crop protection. And I was at a conference seminar a couple of weeks ago, and someone raised their hand and said, okay, what's the next big thing? And my response to that was, actually, we're already in the middle of the big thing, and it's biological solutions. And it's not what those biological solutions are, is a series of solutions which are layered one on top of the other to go away from this kind of blockbuster approach of where you have something that will just kill everything. And so saying, no, we've moved on from that. We're thinking much more as biologists and less as chemists now. And we're creating resilient plant production systems by layering lots of different technologies. And the technologies I'm talking about are primarily macroorganisms, microorganisms, botanicals, and semiochemicals. And globally, there isn't any definition for these technologies. The International Biocontrol Manufacturers Association has these definitions, and that's the closest we're getting to a global definition. And before the Sustainable Use Regulation, the Green Deal, was abandoned in Europe, we could see that these hard headline categories were something that the EU was putting into what they called biocontrol, and they were going to create special provisions for these technologies. So I think it's quite reasonable to follow these definitions. These definitions came about after, in some cases, several years of consultation with experts, with regulatory bodies, with industry, and the wider science community. So they're the best set of definitions that we can have. And just to think again about when we're growing food or we're growing plants, and thinking as biologists, we're essentially talking about an agro-ecosystem where there's a lot of interactions going on. There's a lot of interplay between the soils, between the plants, between the organisms that live on and around those plants. And we sometimes forget that. We forget that this is actually, although it's a monoculture, it still does have complexity, and that we're trying to manage that complexity. And the other thought is, well, is that biocontrol is much more than pest control. We're not trying to kill things. We're trying to manage populations. And if we take the picture on the left of the lacewing, what I'm representing there is a technology. So it was a project in Norway. They found that wheat produces a pheromone that attracts lacewings, and the lacewings then come into the field and eat the aphids. So you're not killing anything, or you're killing indirectly by attracting the lacewings in. And what also happens then is, well, it's Norway, so what happens to the lacewings in the winter? It's cold. So they kind of built up little insect houses and reservoirs to keep the lacewings in the surrounding field. And what you've ended up as a result of this is a more diverse cereal growing area with a wider range of beneficials. And in some parts of Norway, it's over 5 years now since they sprayed anything to manage their aphids. So this is what I mean when saying biocontrol is more than just pest control, that it's a way of thinking about how we manage crops and how we manage food production. And we all know the issues with bees. And a lot of these products that are coming onto the market now, if not the majority of them, are not having long-term or sustained effects on bees. So there's a respect for the environment in the development of a lot of these technologies. And just to substantiate what I'm saying, the Institute of European Environmental Policy did a review of biocontrol and the value of biocontrol. And it's a really interesting report to pick up. The links you'll see in the bottom corner there, to have a look at this. And what they've identified was it's not just about what the biocontrol solutions can do to manage the pests and disease in the crop, that there was other additional benefits. So the most obvious one was human health, that there's less exposure for workers to pesticides. And we all know how hard it is to get compliance with PPE. And so if you don't have things that are toxic, then it makes that compliance easier. So there's a benefit there. So it's a good report, well worth having a read of it. What we can see is a lot of this thinking I'm describing has been translated in the EU into the Farm to Fork programme, which was then translated in through mechanisms such as the Sustainable Use Regulation or Sustainable Use Directive as was, and this then translated into national action plans about how to grow food and how to do plant production well. But it's not just Europe that's moving in this direction. The UN is moving in this direction as well. And if you look at some of the information workshops and presentations that were made last year, they again have come out and said that they believe that the way in which plant production should be done is based on this concept of biological solutions. And something that often surprises me is that I once went to try and find out when was the concept of IPM invented, because I often hear people saying, "Oh, you've got to adopt IPM, this new technology." So I went to have a look, and actually, it's not new. It was invented in the 1950s. It's just taken a long time for us to get to the point where we realise that if we create a system where we're layering in the solutions to manage pests and diseases, we have a more resilient system, and that we have that resilience because of diversity often. So it's not a new concept, but the idea of IPM is just good practice. You're planting the right crop in the right place. You're thinking about how you do that well. You're thinking about your soils, and then you're watching and monitoring really well and using forecasting systems. All this is familiar to us. And then you think about, can you have a mechanical or physical control? And I like to think the example of putting fleeces over carrots to stop the carrot fly going in. Really simple way of managing the insects. And then if you need to, you come in with biocontrol. So again, it's not, you don't automatically come with biocontrol. Follow all these other mechanisms before biocontrol comes in. And then at the very last moment to say, well, if things have got out of kilter because nature does that, and because we have weather patterns we can't predict sometimes, then you need something that's perhaps can work rapidly and to manage and bring the pest population back down below damage thresholds. So as a result of all this interest, the global market in bioprotection, biological solutions has grown. Now, this figure is I've done it from 2018, 2021. In fact, it's pretty much the same now. There's a lot of discussion and argument about how big it is and how fast it's growing. And that discussion sits around what you think of as biological solutions. But what is clear from this is it is growing. It's growing very fast. It still represents a relatively small part of the plant protection market. It's around about 20% of the estimates. Again, a little bit of variability as to whether that's correct, but it's sitting around that. But what we know is it's growing, and it's growing fast. And you probably can't read everything that's on this slide, but this is a representation of some of the companies who are involved in biological solutions. So not just the biopesticides or biological solutions, but also the biofertilizers, biostimulants, inoculants. There's a lot of companies out there. And if we think about what this company's makeup is, the majority of these are SMEs, and of that, a lot of them are micro SMEs. So the types of companies that are getting involved in this industry are very different from the types of companies before. They can be companies who operate at a regional level. They can be companies working at a national level or at an international level. The company size can vary from sort of what I call one man and his dog, all the way up to international companies with thousands and thousands of employees. And all of those are represented and involved to a more or less extent with biopesticide biological solutions. And what we can see, or what I'm seeing is all the time, is this is increasing. The level of innovation, I would say, is gone up at the moment. The difficulty in the marketplace is the money to pick up those technologies, the ability of those technologies to become products that farmers can use, and to move all the way through the system. There's some financial blocks in there, there's technical blocks, and there's regulatory blocks. And the idea with people like myself are doing is working to remove those blocks and to streamline the technology getting forward as fast as possible. But what's clear is there's a lot of companies now. It's very diverse. It's all in every country all over the world now. There's pretty much a biocontrol company. If we look a little more closely in the UK, the biocontrol companies in the UK are most, if not all, are members of the International Biocontrol Manufacturers Association. And here's just some of the logos of the companies who are involved in that. And the reason we come together as an industry group is to exchange knowledge, to exchange ideas, and to help each other to overcome some of the barriers, such as the regulatory barriers to bringing these technologies forward, and also to working and helping to develop IPM programs. So if we think about why the market's growing, what's happening, so I've got sort of 9 reasons for uptake, which are these. what always intrigues me is the top two are often missed off, is that people forget that the technology actually works, that they're good. But something that surprised me is that some of the take up of the technology or advantages are some of the points at the bottom, at the lower end of these, which is that if you don't have re-entry intervals or plant harvest intervals, you can manage your harvest timing better. So if you've got something like strawberries, which in hot weather would possibly be past the picking point within a couple of days, if you had a 3-day or a week re-entry interval. But if you don't have that, you can manage, you're losing less crop, which is an advantage, but also you can manage your workforce better because you can rotate them better if they're not blocked from going into the crop for several days. So working with biocontrol technologies is not just about how well they work and the efficacy, but it's how they can work within an IPM program, how they work on the farm, and how they can be used and taken up on the farm. I just want to take a moment just to go through each of the technologies briefly, just to explain and just so we're all on the same sort of platform of what we're talking about. So we're talking about macroorganisms, we're talking about predators, parasitoids, and parasites. These are some of the microbials that are most commonly in production. So I think there's over 2,000 listed by EPO, but the majority of them are this species that are commonly used by farmers. Here's some of the UK nematode products, which use the parasites. Again, I expect a lot of these are very familiar. And just incidentally, a lot of these have been developed by government-funded institutes like Warwick in the past, who contributed a lot to this, a lot of the technologies that have come forward. So the strategies to use them, there's how do you bring these macrobials into crops? So one of the simple ways is introduction. That tends to be classical biocontrol, but there's conservation. It's looking after what you already have, and then there's augmentation, which tends to be what we're most familiar with. So some nice examples of conservation with putting flower strips into fields where you're looking after the natural enemies that there. My example I also gave earlier about the lacewings. And I quite like this example from New Zealand where they grow flower between the vine strips. And what's happened actually is that the vineyards that do that attract more tourists to them. So they actually make quite a nice income because it looks prettier than not having the flowers in it. So bit of an incidental, but quite interesting. So you look after what you've got, but then there comes to the intentional release, the augmentation. And what we're familiar with is probably some of these types of technologies where the live organisms are put into the crop. There's different mechanisms where you perhaps hang a card and the insects can walk out themselves, other times where you distribute them over the crop. And increasingly, the technology for how they're distributed, how they can be moved into the crop, is getting better all the time. Then if we think a little bit about microorganisms, so this is a list of just some of the species which are commonly used. So these are microorganisms which are the active substance in a lot of the more common microbial-based products. What you have to be careful here is they'll always come with a strain name, and it's the strain that's actually quite important rather than necessarily species. There's two reasons for that. Is because strains can differ in their ability to manage pests or diseases, but also because taxonomists change the name occasionally. So like Metarism anisopoli is now actually Metarism bruneum, but if you know it's the F52 strain, you can look for that and you can make sure you get the same product each time. And the microorganisms may be composed of the microorganisms, which viable plus or minus secondary compounds which the microorganism produces. Different companies do different things. And we've got microorganisms which work against fungal diseases or against bacterial diseases. We've got microorganisms, fungi that work against insects. And we also have viruses that work against insects, and we also do have bacteria that work against insects. So you've got representatives of all the microbial groups that are active against the disease or the insect. A new set of technology that's coming along now, which is quite interesting. These are viruses of bacteria. So these are for bacterial diseases. And some of the bacterial diseases are really quite hard to manage. So bacteriophage or bacterioviruses coming to the market. We haven't got, they're beginning to come into Europe. so potentially coming into the UK, but here's some that have already been approved in the USA. And you can see from this that some of them have been around for quite a while, 2011. But this is an interesting set of technologies because of their ability to deal with some of the more tricky bacterial diseases. The other thing to think about when you're working with microbes is what they are and where you place them. So I'm just trying to illustrate in this graphic here is that for an insect, for example, some of the bacteria and fungi, viruses, some are going to go directly through the cuticule, but some are eaten. And knowing this is important because it helps you to understand where to place the product in the crop and what the likely interactions are. So it's quite important to understand this about any microorganism-based product. And the other thing about the microorganisms is they have multiple and complex modes of action. So this representation is for trichoderma, and it's shown that there's 5 different types of modes of action. And all or any of these, or one of these, can be operating at one point in time, depending on the plant, the disease, the strain, climate conditions, etc. So it's the ability of a microorganism to manage the pest or disease is the sum of all of these components, it gives resilience because it means that you can have different modes of action going on depending on changes in the crop conditions, but it also makes it much more complex, increases variance with some of these products. And something that I often hear when I'm thinking about microorganisms, particularly from regulators, is just thinking a little bit about microorganisms when you put them out there, the disasters, etc., that should happen. I don't think we should lose sight of the fact that plants, every breath we take, everything is absolutely covered in microorganisms already. It's not as though you're putting them out into a sterile environment. This makes it hard to get them to work sometimes, but it also, from a regulatory point of view, you're not putting something out where you won't have a moderating effect of the microorganism-based product. It also is some of the reason why you don't get long survivability of microorganisms, because there's not just abiotic factors such as UV, desiccation, but you also have other microorganisms attacking the microorganisms. So it's worth just remembering that and thinking about how you use them. Just a few examples of the biofungicides that are currently available in the UK. Here's the insecticides that are available in the UK. I'm moving through them fast because you'll have a copy of this presentation. Then if we think about the botanicals, I mean, they are what they say they are, and it's natural substances. So if we think about botanicals or plant extracts, these 6 plants are the source plant material for products that are registered in Europe, and some of those are registered also in the UK. When you talk about natural substances, you might be talking about things like diatomaceous earth, and it's a wider group. And what's also coming into this group is some of the new technologies. So what's known as the double-stranded RNAi, the peptides and the proteins, they'll fall into this natural substance group. These are new, there's less of them come forward so far. There is experimental work going on at the moment to test the regulatory system. So probably the best example is an RNAi product developed by a company called Green Plant, who just before Christmas got a US registration for a sprayable product based on the RNAi for use against Colorado potato beetle. But judging by the number of companies involved in this, the amount of research activity, I think we can expect to see more of those technologies coming forward quite quickly. What's true about botanical plant extracts and also about other natural substances, again, multiple modes of action. Some of them can be physical. They can be very simple substances, or they can be highly refined. So cold pressed orange oil is 98% limonene, but you've got other plant extracts, which, each component in that whole extract it represents, 1, 5%. So you've got sort of 20, 30, 100 different components in there, and it's collectively how that all works. So again, sort of fairly complex substances. Just a few examples available in the UK. And then lastly, moving on to semiochemicals. What we know most about semiochemicals chemicals is the mating disruptions, and that's the ability of one organism to produce a compound which affects other members of the same species. And these can be deployed as mating disruptions, so males unable to find females. You can lure and kill, where you're attracting the insects to an insecticide, and that can be a bioinsecticide, a chemical insecticide. All those mass trapping, you're attracting the insects into, say, a water, and they drown in the water. And for that mass trapping, you're probably using chiromones, so they're feed stimulants. Majority, the best known of pheromones are the straight chain lepidopteran pheromones, the SCLPs. These are the mating disruption compounds, and you'll see these traps in, for example, apple orchards, where the pheromone is being secreted that mimics the female pheromone. The males can't find the females, they can't mate, you don't get the next generation. But there's also a lot of development now for microencapsulated formulations to develop sprayable formulations of the pheromones, and these are looking at a wider range of target pests in a wider range of crops. Something that I often get asked is, and I often hear said is, oh, biocontrol doesn't work very well, it's not very good. And so I kind of raised the question to you, and I mean, about what we mean about something working. What do we understand by what's efficacy? Are we asking how it works in an IPM program? Are we asking how it interacts with the chemical pesticides? What effects are we looking for? Are there disadvantages of using these biocontrols, or are there advantages? So when we talk about something working, it's actually quite complex. It's quite a big question, and it needs us to think through in the context of IPM about what we mean by that. A lot of the time people will sort of say, oh, you don't get 80% control, and that may be true. So just thinking about it, do biopesticides work? And I'm not going to be able to see your hands, but maybe you can just reflect a little for a moment and say, well, what level of effect are you looking for if you're running a trial, for example? What level of efficacy would be acceptable to a farmer? And what level of efficacy do regulators need? So what level of effect you should get in trials depends on your trial design. That's entirely up to you. What level of effect the farmers? When I did some research with some very early projects which HDB funded, what I found out is it wasn't the amount of efficacy that was important, but the fact that it needs to be consistent. And a lot of farmers are saying, I can work with 50% if I know it gives me 50% consistently, and then I can work out how to put it into my IPM program. So again, this argument that you need a high level of efficacy, not necessarily been true. And then for the regulators, often it's considered that a regulator is going to prove something unless it's above 80%. That's not true. There's a dogma going around. There's nothing in any guidance document anywhere that says you must have that effect. What you must have is demonstrate a net benefit from using this product. And if you have something that isn't toxic, isn't causing environmental harm, isn't causing harm to non-target organisms or to humans, then the net benefit is easier to prove that. And that's why we see a lot of biocontrols coming into market. They have a lower level of effectiveness, around about, generally I'd say it sits between 40 and 70%. Occasionally you see something that does higher. BTs certainly do higher than that. But what I'd also argue is the evidence I've seen, and I've run a lot of field trials, is you don't need it to be more effective than that. What you're trying to do is just pull the population down below the damage threshold, and using the products judiciously within an IPM program, they are able to work well to manage pests and diseases. And to back up some of what I'm saying about the 40 to sort of 70% efficacy, this is just some products registered in the UK, and these are the levels of efficacy that were given to me by the manufacturers. So we can take something like ASO, which is one of the leading microbial biofungicides out there, and you can see there's not a claim that it gets anywhere near 80%. It's claiming sort of around about 60%, and yet it is one of the leading brands. So it just substantiates that you don't need that level of efficacy. And also just emphasizing, again, not having a level of efficacy, the dark blue line here represents a modeling where you apply about a product that has about a 30% effect, assume population regrowth, but just shows that if you put something in that reduces the population by 30% and you keep doing that, you're going to reduce the pest population below the damage threshold. This is a very simple principle of IPM. And just another example to pick up on here about what these microorganisms can do, because we tend to think that they are best used in, say, a protected environment, in specialty crops, and that it's not true that that's where they work best. It's true that that's where they were first adopted because of pressure from losing substances, but also from an interest in adopting new technology. So this is an example where Trichoderma aspera strain T34, which is registered in the UK for Fusarium, a company based in Eastern Europe picked this product up, used it as a seed treatment, and they found that they could reduce the levels of sclerotin, Fusarium, and mycotoxins to below the levels that the chemicals could when used as a seed treatment. So again, it's opening up that a lot of these biocontrols have a role within broadacre as well as within specialty or horticulture crops. Another example of a project here is a project run by the Yorkshire Agricultural Society. They have a farmer science network, and they posed the question, could you grow cereals without synthetic chemical pesticides? So we conceived a 3-year project, and in that 3 years we ran 3 trials in every year, run to GLP by an independent organisation, Eurofins, and what we did is we compared IPM programme to chemical programme to a biological programme. We did that in the northeast of England at 3 trial sites. In the first year, we could find no difference between the treatments, so we refined the trials a little bit more, improved the replication. In the second year, again, we didn't find a difference between the 3 sites or between the treatment regimes. We did, however, note that in some of the biological treatments, the wheat had moved from a feed wheat to a bread wheat, which is because it had a higher protein content, which was a positive attribute. And then in the third year, we started to get some additional differentiation, but broadly saying there wasn't such a significant difference between the sites and between the programs. So where did we get to at the end of that? Was I think, are biological technologies for wheat realistic? And the answer is yes. More work to do, looking at how do you apply them economically, what would the costs look like, how do you capture that benefit of an uplift in protein content. So it definitely needs more work, but it proves the concept that biocontrol will work in that broadacre situation. There's something that's also coming along that unlocks the biological technologies is improvements in application. So this is an example of a project, again, in Norway, where they're applying herbicides or bioherbicides. So they've looked at this with glyphosate, but they've also looked at this with acetic acid and pelargonic acid. And what this machine does, it's able to sense and tell the difference between weeds and crop. It's then also able to sense where to place the product. They've got a different droplet delivery mechanism. So what's happening is this type of technology is taking something that wasn't selective and is now selective. It also reduced by over 80% the amount of active substance that need to be applied. So you start to see that it's changing the economics. So we need to think a little bit about the questions we ask and how we change that. How do we deliver these biocontrols into the crop well? How do we place it in the crop well? How do we optimize them? So I think something that's going to unlock a lot of the biocontrol agents is the application technology, which is combined the sensing technology and the droplet delivery. And this is just one example, but there's a lot coming onto the market now. And as you can see from this one, it's unmanned. It's running. This one actually runs, I think, on fuel still, but there's a solar model available. These can run around the field. They're working on a GPS system. They can run around the field. They're just controlled from the central office in the farm. And then I want to sort of touch on to the regulatory framework a little bit. Me, amongst many others, just find the regulatory framework frustrating at times, but equally as a citizen, I do believe that we should have a regulatory framework. And that regulatory framework includes the protection of the intellectual property rights for people who've done all the research and discovery, protection of biodiversity. If you've discovered something somewhere, that you the rights, there's equitable sharing of the benefits from that exploitation of that technology. You have import and export restrictions, which is ACRE here in the UK. And then you have plant protection product registration, which is what CRD, HSE CRD operates. And the basis of this is that biological plant protection are different from conventional chemicals, so we need a different approach. Increasingly, there's global harmonisation with regulations, so FAO set regulations which are widely adopted, OECD provides guidance which is widely adopted, so does the EPO. And we can see that there's increasing harmonisation in places like the US and Canada, in places like West Africa. And we forget that Europe is an example of harmonisation. Imperfect as it is, it's 27 member states agreeing to harmonise together with one system. What makes regulation a little tricksy sometimes, and it's mainly this philosophical concept. In the EU and in the UK, we apply the precautionary principle, and in the USA, generally regarded as safe. So the EU, you're always having to prove a negative, and the US would say, we think this is okay, but just keep monitoring and let us know if something's different. So that makes a difference in this, how you do registration and the consideration and the checks and balances needed. So what gets regulated is, I've mentioned the access and benefit sharing. So what's in green is all of these substances are registered by the same system as the chemicals and follow the same system, but there's adaptations in the information that's requested to allow these to be registered. Biostimulants are not currently requiring registration in the UK. That may change. So most of the products that are going to come into the UK are going to come through Europe. So what's happening in Europe? So Europe timelines in theory should be taking 2.5 to 3 years. In practice, 5 years and longer, which means there's a real bottleneck in technology coming forward, which means there's a lot of things that's sitting in Europe that weren't approved at the time of Brexit. So the question is, how do we attract companies to bring these into the UK as well? Especially as the UK requires the same authorization. So for companies coming in, they have to pay for the EU and they have to pay for the UK. And the question is the market size big enough in the UK for companies to do that? So if we look around the world, what we can see is the EU really does stand out as being one of the slowest regulators in the world. By a considerable amount. The EU recognises this and has been making funding available. And some of the mechanisms that you can have for that that have been discussed are things like, why do biocontrol technologies not sit on a different pile? Why do they sit behind the chemicals? So if you've got trying to work your way through chemical dossiers that take a lot of time because they're very large dossiers, they're not very complex. And your biological may take you a month to evaluate as opposed to 12 months. It sits behind the chemicals. So there's a concept now that the biocontrol solutions sit on a different pile to the chemical solutions. They have their own timelines. They have their own specialists. And we're starting to see that is improving these European timelines. That's just one of the mechanisms the EU is following. What also to say is you need to have skills in the registration of biocontrol technology. And I think what this shows is across Europe, there's different member states have different experience of dealing with biocontrol. And that's important for the training of the regulators and the technology, but it's a bit of a chicken and egg. So why will they train unless they get the dossiers, but they're not going to get the dossiers unless they're well trained. So there needs to be a way to break that. The EU has broken that by providing money for training of the regulators in the new technologies. So if we look at what's available in Europe, ignoring the 2009, because that was a cleanup process. So they just cleaned up the legacy, and that's when the new regulation came in. But if we look in a little bit more detail, we can see that the throughput of technologies, biocontrol technologies coming forward, has not really changed that much, despite facilitation, despite there being a demand for these products. There's still a bottleneck. They're not coming through the system, which means they're not coming to the UK either. If we look at what's available, you can see that most of the products have come forward are for insects and diseases, or sort of equally very little for weeds or nematodes. But what is clear is that over 40% of the active substances that go forward for approval are biocontrol agents. So again, it shows that there's a lot coming forward. Now, in terms of products and the use, again, biocontrol is sitting around about 20% of the use. So they're not, there's less grower uptake, but in terms of active substances, more and more products becoming available. And since February 2016, there's more biologicals coming forward than chemicals. And if we look here in the UK, we can see that the number of active biocontrol active technologies coming in up to 2018 has increased significantly. The reason why you don't have lots of products is because there's usually a 1-to-1 ratio between the active substance and the product, and that's different for chemical pesticides. So the products and the active ingredients track each other much more closely. So looking just in the UK then, most of the biocontrol technologies are for diseases, some for insects. Most of them that come forward are microbials, far fewer natural substance botanicals, and very few semiochemical. And I think it's noticeable here that of the products that are available, of the 3,000 products available to farmers and growers in the UK, only 103 of those products are biocontrol. So there's quite a lot of work to do to get these adopted more widely. And if we look at what's out there, what's available in the world, what we're starting to say was, how do we get these into the UK? How do we attract companies to register their products in the UK to support UK farmers to be able to adopt IPM deeply? And then lastly, I sort of want to touch on a little bit about the EU regulatory process. So we all heard about the sustainable use regulation. We all heard that that was dropped, and the pesticide reduction targets. One thing that also got dropped in that was there was significant provisions to make it easier to bring biocontrols to the market. So there's provisions to have provisional approval, to have the fast track system, to have additional funding, provide additional expertise, and that also got dropped as well. So whilst a lot of people may feel, it's great that we've dropped those targets, it actually has had an impact on biocontrol. As a biocontrol industry, we're working very hard to find other ways to bring some of these provisions forward so we can keep working to unlock the bottleneck for biocontrol availability. And unless it's unlocked in Europe, it's not going to get unlocked in the UK either. We're sitting behind all of this. So just summing up then, I think what, for me, biological or biocontrol solutions are, this is us moving around to biological-based crop protection. It's difficult because it requires all these disciplines to work together. It requires a lot of knowledge, and it's very knowledge intense. It's about moving knowledge around as well. And yes, we will still need some chemistry, but we've got a lot of work to go yet to improve biological-based crop protection. Thank you.
Excellent. Thank you very much, Roma. That was a fantastic overview. So we've got one question in the chat. Can you see that, or shall I read it out to you? It's about
I'll read it.
Norway, about the robot.
Okay, yeah. Yes, okay, does it mix and deliver at the same time? Yeah, there's two versions. There's one where you can put the pesticides you think you'll need it already mixed, but there's also a version looking at like a dosatron where there's the water and the active substance or the product separately, and then it mixes as it delivers. So they're trying different versions. Yeah, and how much to mix before setting off the field? Well, that's the same calculations as, they've run it a few times, so they know how targeted it is, so they know what they're delivering per hectare. And they've primarily worked on herbicides, but there's the potential also to work on insecticides and fungicides, and so they know how much they do experimental work to understand how much they need to deliver for the crop pest situation and for delivering crop and reducing waste.
So do they scout first? Surely the amount you use is going to depend on the individual situation, I would argue. You could have even the same field in a different year is going to have a different weed burden.
Yes, it will have. So the machine senses as it goes along. So the equipment is preloaded with more than it needs, and so the machine sensing what weeds are in there. But again, you have that build up of knowledge of the field, because the data from the machine when it's run is collected and held. So you could potentially run it without spraying to get a measure of what the weeds were before you went out if you wanted to. The only cost to the farmer would be the fuel for doing that. So the trick is the very sensing technology.
Yeah, because I know now, like in the SFI, they've you can now get a payment per hectare for using kind of enhanced spraying. So I guess green on green on green or kind of sensors as you go. But then if you're kind of retrofitting that to a traditional sprayer,
it's not a retrofit. It's a specific piece of equipment. So I think that's what the change is the specific equipment that's really designed for. The trick with that Kilter one is they have exceedingly good sensing technology. It's not just any, it's very, very good. I mean, actually, what they also do, they're the airport sensor people. They design the sensors in airports. So it's smart technology, and that's the trick. Is this smart technology coming? They didn't come from agriculture. They came from a different direction. They were engineers, and I think that's what's beginning to unlock things. I'm just aware, Sam, there's more questions.
Yeah, sorry, go on.
Yeah. So the question from Gary is, the lure and kill technique is very attractive, but very few products have been commercialised. No, it's not about the wind, it's about the market for, so is there enough market for the pest to justify the development, where you've got to think about the regulatory costs that are in there for developing it. So this is where the regulatory costs need to be reduced to make those opportunities economically viable. So it's not about the wind, it's about the product development costs. From Ian, there's a question, is what is the percentage of biopesticide to conventional sales in your estimate currently? As far as I'm aware, Ian, I think it's sitting around about the 20 to 80% generally, but obviously within different market sectors, that ratio changes. So I think in horticulture, you'd expect that ratio to be much higher, biocontrol to chemical.
Great, thank you, Roma. I think we better move on now. So our next speaker is my colleague Dave Chandler, who I'm sure many of you know, and who is Warwick's expert on biological control. So over to you, Dave.
Yeah, I was just gonna, hi everyone, I was just gonna give a few slides. It's a bit like what we did when we did the last webinar on kind of agri-tech, and it's just to give kind of our Warwick kind of crop centre perspective. Rosemary, can you see that okay?
Yes, fine, Dave.
Yeah, good. Fine. So so it's just to kind of give our our perspective and general thoughts on biocontrol. And I did this independently of Roma, but actually what I'm going to kind of talk about is complementary to what Roma is talking about. I'm just going to turn because I've got multiple screens. We're just you'll see the side of my face here. So I think Roma said this. So we're actually dealing now with a very wide range of plant protection products, and biocontrol covers a wide range of entities. So we have at the bottom, I've labelled everything with a green B for biocontrol, but we have our macroorganisms, our microorganisms, our natural products, and also nature identical chemicals. These are really important. So the ag chem companies are investing a lot of money at the moment to screen microorganisms for metabolites with pesticidal properties that they can develop as plant protection products. And I think really, rather than think necessarily of a clear separation between biocontrol and other forms of plant protection, we need to kind of think of a continuum, if you like, moving from kind of traditional synthetic pesticides to nature-inspired chemical pesticides. You know, we already have pyrethroids and things like that, but we need to think of a kind of a continuum, moving from kind of chemistry to biology. And the point about that is that in future crop protection, we're dealing with a very wide range of entities. Each entity has its own characteristics that are going to determine its performance, and the crop type is going to be critical, indoor versus outdoor crops, for example. And to me, that upshot is that a lot more, Roma touched on this, is a lot more kind of knowledge required for crop protection, both kind of in-house expertise from growers themselves, from specialist agronomy advisors, and also from the R&D thing. And for horticulture, for UK horticulture in particular, now we no longer have HDB horticulture. I think that's quite a serious challenge that we need to address, both in terms of generating the knowledge and also disseminating the knowledge to practitioners. So you've seen this already from Roma. This is the IBMA pyramid, and I just put in some kind of generalizations from our perspective. So Biological control, as we've seen, is well established and protected crops, and the challenge for the UK is moving biocontrol into that outdoor crop market, particularly for field vegetables, I think. And the kind of the most obvious step forward is going to be using the natural products and kind of the nature inspired chemistry, because that fits in with existing kind of methods of crop production. But if we're going to do that, then we must use them as part of IPM. Otherwise, if we don't, and if we rely on those chemicals too much, then we're going to just end up with selection for resistance for them. So the way to minimize the evolution of resistance in target pests and diseases is to use them as part of IPM. And as Roma was saying, don't ignore the living biological controls. There are more challenges to actually using biocontrol in outdoors, because the physical, the abiotic environment is different and can be more challenging, but they can work. We just need to be doing more of it. And a key part is to actually develop a strong evidence base for biological control. Surprisingly, we don't actually have a kind of a holistic science of IPM, by which I mean we don't fully understand how the different components of IPM actually work together, in particular to try and identify where we get true synergies, so things have reinforcing effects on each other. And that's going to be really important aspect of R&D in the future. So at Warwick, for example, we've been doing work in the last few years to investigate how we can use ants and host plant resistance to kind of make biological control work better. And I think that's going to be really important for the future. Roma already talked about this. In biological control, we tend to use inundation an awful lot, but we shouldn't ignore kind of inoculation, where you're applying biological control at relatively low levels, and you allow the biological control agents to persist and to multiply within the pest population. And conservation control is really important. I'll come on to this in the next few slides. So in terms of developing biocontrol strategies as part of IPM, this is really old work, but that we did a long time ago, but I think it illustrates the points really nicely. So this is work we did with Rob Jacobson at Stockbridge back in the day, when we were using a fungal biopesticide based on the insect pathogenic fungus Bavaria bassiana, and using that as a second line of defence as a supplemental treatment, combined with phytomites for control of red spider mite as a replacement, as an alternative for fen-butadiene oxide. So we did a crop scale experiment in which we infested tomato crops with red spider mite. We used phyto for the control of red spider mite, but we simulated a situation in which we had relatively low levels of phytomites, so we would have to come in with a supplemental treatment, and we compared fen-butadiene oxide, which was available at the time, with Bavaria bassiana. And this data is just for number of adults, nymphs and eggs of spider mites on there, and also phyto levels. And the little stars, just the asterisks, are showing where we get a statistically significant effect. And the point about this is that in this case, the biopesticide was actually outperforming the standard chemical treatment at a time. And I think an important point is that you can use relatively simple strategies within an IPM pyramid framework to get reinforcement and to get very effective pest management. And certainly I would see that the biopesticides have a big role to be used as supplemental treatments for primary biological control with the macros. So that's just an example of that, and I'd like to see much more of that kind of work taken forward. I can go through this quickly because Roma already showed a similar slide to this, but this was work on conservation biological control in Switzerland. This is where people applied flower strips in potato crops, and the flower strips were attracting natural enemies in, hoverflies and lacewings. They were having a significant effect in retaining natural enemies within the cropping environment, and that had a significant effect on causing a reduction in the number of aphids within the crop itself. And it's something that we should be utilising much more in the future in field crops within the UK. This next point is about biopesticides. Roma already mentioned about application, and for biopesticides, many of them have contact activity, and then they're not forgiving like conventional old style chemistry, so you have to really be on it. And this is so important. You have to be really careful and as good as you can be with your spray applications. This is work we did in that HD Amber project, work done by our colleagues at Silso Spray Applications Unit, and it looks at the effect of water volume on the amount of material deposited at a crop. And this graph here shows a graph of water volume, and this line here shows the total amount deposited on a crop when you're applying a kind of a fixed concentration. And basically the idea is that the more water you apply onto the crop, then the more material is going to be deposited onto crop, but it plateaus and there's a limit, and so there's a limit to the amount of material that can be deposited onto the leaf, because after that you start to get runoff and you're losing material. But if you look at this line here, this is the normalized application, so that's the amount of material per volume of water. And here you can see that the more water you put on, your application effectively becomes less efficient. This is really important because at the moment for biopesticides, they have quite a broad range of water volumes which are allowed on the label. So basically it's the grower that decides the amount of water volume that can be used, and the recs go up to about 1500 litres per water for nominal constant dose applications. But we've shown in amber that the amount of material that is retained on the leaf, even at a nominal constant dose application, is actually sensitive to water volume, and that impacts on efficacy. And growers logically tend to think that if you apply a higher water volume, you get a better coverage of the plant and better results. But actually the opposite is true, and you want to be minimizing the amount of water volume, because there you avoid runoff. You actually get a higher concentration of product on the plant and the target, and it's more efficient because it takes less time to spray. So all biopesticides have an optimum water volume for efficacy, and water volume has a direct impact on efficacy, but unfortunately we often don't know what that optimum water volume is. And I think we need to do a lot more work to actually optimize spray application, in particular to work out what the optimum water volumes are. Finally, I just wanted to link this to some of the work we're doing in agri-tech. So Roma again talked about this. So I think kind of agricultural engineering technologies are going to have a major impact on biological control, whether it's automated crop monitoring systems to be able to do more enhanced automated pest and disease spotting. So you're kind of partially replacing the work of manual crop walking. The use of things like artificial intelligence to improve pest and disease forecasting, but also to identify where we're getting the synergies within IPM, so we can actually work out the best combinations of crop protection agents to use within the IPM pyramid. Precision automated applications, so Roma talked about with the herbicide things. So in Warwick, we already have a part of our agri-tech entity, we have an existing project to develop one of these robot herbicide weeders, and I think you're going to see a lot more of these coming through in the future. And then finally, something that's absolutely critical is more work on mass production and smart formulations, because the big question is how we're going to be able to produce enough of these biopesticides and biocontrol agents in the future to meet demand, and we're working actively on that in early stages as part of the kind of our Warwick Agritech entity. So that's all I wanted to say on that. I can finally stop sharing my screen on that. As I said, it was just a quick run through to kind of reinforce some of the things Roma was talking about from our kind of Warwick Crop Centre perspective.
Excellent, Dave. That was a great follow on to Roma's presentation. So I don't think there are any questions in the chat. Does anybody want to ask a question at this point? Say you can either put your hand up or shout. No? Okay. Well, Roma's very kindly just sent us her slides, so we'll put them up on a web page. We'll also put the recording up there as well. If you have any questions following on, then yeah, please forward them either directly or we can forward them, and I'll send out an email about basis points as well. So thank you again, Roma and Dave, for really informative presentations. It's just great. And thank you everybody for joining us, and hopefully see at least some of you at the next event in March. Thank you. Bye.
Bye.